Hello students, so welcome to the lecture series on filter design by Edmingo team. So this lecture series will be helpful for GATE and other competitive exams. This will also be helpful for the college students of Electronics and Communication Engineering (ECE). So this is actually the part of signals and systems, and it is also in the GATE syllabus. So in this lecture series, there will be two sections. There are two sections. One is IIR filter design, where IIR means infinite impulse response, and the another section will be FIR filter design, where FIR means finite impulse response. Okay, so we'll be talking about how to design IIR filters and how to design the FIR filters. So we will be talking about, first of all, IIR filter design. Okay, infinite impulse response filters. Now what is the meaning of infinite impulse response? So very simple meaning is that the filter is actually a system, okay, generally an LTI system. So any filter is a LTI system, and if the impulse response of the filter has, I can say, if the impulse response of the filter is non-zero for infinite values of n. So let us say impulse response, in bracket I write Hn. Okay, so Hn is the impulse response. If it is non-zero for infinite values of n, then it is IIR. And if Hn is non-zero only for few values of n, then it is FIR filter. Okay, very simple. Now one more thing that we can recall, that is, if Hz is the Z transform of Hn, then if Hn is non-zero for infinite values of n, then Hz will definitely have a pole at a finite location, or I can say will definitely have a pole at a location other than z equals to 0 and z equals to infinity. For example, u of n, it is non-zero for infinite values, So its Z transform is 1 upon 1 minus Z inverse. So there is a pole at Z equal to 1. Another example, a to power n un will have Z transform 1 minus a Z inverse, where pole is at a, Z equal to a. So we can say that if Hn is non-zero for infinite values of n, that is filter is IIR, then Hz will definitely have a pole at a finite location or at a location other than Z equals to 0 and Z equals to infinity. So it's a very important point. Okay. Another important point is, so this can be a question, that IIR filters will definitely have a pole at a location other than 0 and infinity on the Z plane. Okay, so this can be a question, or this can be asked in a true or false statement. Okay, something like that. Similarly, an FIR filter where Hn is non-zero, Hn is not equals to 0 for only finite values of n. So in such cases, Hz, that is Z transform of Hn, will have, okay, so I will explain you this. Before writing, let me explain you the statement. Now you recall that Hz, so let us say that Hn is a FIR filter. Now since it's a FIR filter which is non-zero only for finite values of n, so the summation, that is Hz is equals to Hn Z to power minus n equals to minus infinity to infinity. Now we know that what is ROC? ROC of Hz is the values of, so we know that Z is a variable that has magnitude R and angle is, or phase is sigma. So let us say this is the phase, I call it sigma. Okay, so this equation can be written as Hz is equals to n equals to minus infinity to infinity Hn R to power minus n e to power minus j sigma n. Now the ROC of Hz is the values of, so let me write it here. Now if you recall the simple Z transform, then the ROC of Hz is the values of R, where the summation of equation number 1 is less than infinity. That is, so I am writing equation number 1, that is this summation. Okay, so this summation should be less than infinity. Those values of R is called the ROC of Hz, where Hz is the Z transform of Hn. So I hope you all know this. So now since Hn is valid, or I can say Hn is non-zero for only finite values of n, so equation number 1 is valid for all values of R except 0 and infinity. Okay, except 0 and infinity. So I can say that, so for a signal Hn which is non-zero for finite values of n will have ROC entire z plane, entire z plane except z equals to 0 and infinity. Okay, so this is important. Now as we know the property of ROC, that is ROC never contain a pole. So we can say that since the ROC of a signal Hn which is finite, which is non-zero only for finite values of n, is entire z plane and ROC never contain a pole. So combining these two properties, that is this property number 1 and this property number 2, so from property number 1 and 2 I can say that the pole of Hz, that is Z transform of Hn, will be at z equals to 0 or at z equals to infinity or both only. It cannot be on the finite location. Okay, so this is a very important conclusion for FIR filters, that for FIR filters the pole will be only at 0 or infinity or both, and no finite valued pole will exist. So if I write conclusion, very important conclusion that might be asked in a statement format is that, so here Hn is non-zero for infinite values of n, Hn is non-zero for finite values of n. Second, has to have a pole at location except 0 and infinity, means or in a better words I can write, has to have a pole at location other than 0 and infinity. So 0 and infinity can also be there, but there has to have a pole between 0 and infinity also. So next, in FIR we can say that has poles at z equals to 0, infinity only. Okay, so this is very important. Okay, now so this is enough for IIR and FIR. This much is enough for the information on what is IIR and what is FIR. Now let's move on to the filter design of IIR filters. Okay, now what is this? So how we do the design of the filter? So what is the method? First of all, we design the analog filter and then convert it into the digital filter. So why we do this? Because the designing of the analog filter is very much advanced. So that's why for filter design, first of all, the digital filter is designed in the analog format. So I'm dictating it. So first of all, the digital filter that is to be designed is actually designed into the analog domain, and then the analog domain filter is actually converted into the digital filter that is required. Okay, so here we will be studying, here we will study how to transform analog filter into the digital filter. Okay, now this is very important. This is the motive actually. If you can say that this is the motive of the lecture series. Okay, so this is the motive. Okay, and the question that will be asked will be on this format only. Like the analog filter will be given, and it has to be converted into the digital filter. And since there are three methods to convert this, we will be studying all the three methods in the lecture series, and that will be sufficient for you. Now, first of all, let's look at the requirements of the. First of all, let's look at the requirements for transformation. Okay. Now, since what will be given to us, the analog filter, and always the analog filter will be given as in the transfer function format. So transfer function of the analog filter is ys upon xs, and it is given in the format summation k equal to 0 to m dk s to power k divided by summation k equals to 0 to power n 0 to n ak s to power k. So this is the transfer function. Now if we convert this transfer function into an equation, so it can be written like this also. Okay, so if I convert this equation into time domain, so as we know that if yt has Laplace transform ys, then dyt by dt will have s times of ys, and if you do the kth derivative on the left side, so you will multiply s to power k by s. Okay, so this equation number 1 can be converted into time domain. So it is written as ak dk over dtk by yt is equal to summation equal to 0 to power m dk. Okay, so this is the time domain equation of the above equation. So this is the time domain. Okay, now there are three methods to do the conversion. We'll be studying all three methods to convert analog filter into digital filter. We'll be studying all the three methods. Okay, now first of all, let's look at the requirement, because these requirements can be asked in the question. Okay, so an analog filter HAS will be causal and stable. So what is the condition of causal and stable in the analog filter? The requirement is that all the poles of HAS should be in the left half of the S plane, okay. All the poles should be in the left half of the S plane. Now if you look at the requirement of the digital filter, for causal and stable, all the poles should lie inside the unit circle, okay. So the transformation, if you look at this, these two statements, this is statement and this is statement. So this is the statement number one, and if you look at this statement, all the poles should be in the left half, lie in the unit circle. So these two statements, if you compare this statement and this statement, then you can say that, so the transformation should be such that left half of the S plane should be mapped into the region inside the unit circle in the Z plane, okay. Okay, plus we can add one more thing, plus the imaginary axis of S plane should be mapped into the unit circle of Z plane. So these are the requirements. So any competitive exam or GATE exam also can ask you in a one marker question these requirements, okay. So that's why these are important, okay. Okay, so these are the requirements. And now one more fact about, so I left out this, so if I have space, okay. So I have one more comparison which can be done. So let me add a page here. Because these are the notes that I will provide you, so I cannot like ruin them. So that's why in a systematic manner I will shift it downwards, and now I can write it here. So one more difference I want to add here. There is a very important difference between the IAR and FIR filters. Now as you know that IAR filter will have a pole. So for example, let us say Hn is a to power n un. So the Z transform will be 1 on 1 minus a Z inverse. So by taking the discrete time Fourier transform, e to power j sigma will be 1 upon 1 minus a e to power minus j sigma. That will come out to be 1 upon 1 minus a cos sigma minus j sin sigma. So this can be written as 1 minus a cos sigma plus aj sin sigma. Now if I write the phase of this IAR filter, so it can be written as into magnitude format 1 minus a cos sigma whole square plus a sin sigma whole square under root, and the phase can be written as tan inverse imaginary part upon tan inverse a sin, I have to shift this more, a sin sigma divided by 1 minus a cos sigma. In the if I take this in the numerator, so h e to power j sigma can be written as 1 upon under root whole square plus a sin sigma whole square, and that will be minus times of tan inverse a sin sigma upon 1 minus a cos sigma. Now similarly, if there is a pole, a finite location pole, whenever there is a finite location pole in Hz, then in no case you can get a linear phase of Hz or a linear phase of h e to power j sigma. You will never get that. So what is the meaning of linear phase? The linear phase means, let me add one more page. Okay. So the linear phase means of Hz or h e to power j sigma means phase is of the format a times of sigma. Okay. Okay. So phase should be of this format where a is any constant. It can be positive or it can be negative, but it has to be in this format for linear phase. And thus, whenever we have an IAR filter, Hz will have a finite location pole, or by this word finite location pole, I mean that there will be a pole between z equals to 0 and z equals to infinity always, and thus h e to power j sigma will never have linear phase. Thus we can say that a realizable IIR filter will never have, or I will just write that statement, that will always be true. Okay, so the statement is physically realizable and stable IIR filter cannot have a linear phase. Okay, but the FIR filter can have that. So we'll be looking at what are the conditions for FIR filters to have a linear phase, but in the later part of the lecture series. But till then, this is a statement that will be true. If you find this kind of statement, then it will always be true. Okay, but this can be asked in any of the GATE exam or any other competitive exam also. So we have done till here. So in this part we will start with method 1 of IIR filter design. IIR filter design. Okay. So this method 1 is actually called as design of IIR filters by approximation of derivative. Approximation of derivative. Okay. So this is the name. Okay. Okay. So let us first start with an analog filter is given. So an analog filter is given to us, and it is defined by k equal to 0 to capital N AK. Okay. Now, as we know that differentiation of yt at t equal to nt, okay, at t equal to nt will be given as y nt minus y n minus 1 t divided by capital T. Now here t is actually, so we are actually sampling yt. So we are sampling yt. So here, so we have to convert this analog into digital now. So we will be sampling the signals. So here capital T is the sampling interval, and if we sample yt, then we get ynt. That is, we replace t by n capital T. So small t variable is converted into n variable multiplied by capital T, where n variable is always an integer. Okay. So in this equation, dy t over dt at t equal to nt. Now ynt is generally written as yn. Okay, because this t is a constant. This t is a constant, that is actually the sampling interval. So this is the constant, and here n is the variable. So what is the variable here? N is the variable, t is a constant. So that's why it is written as yn, where n is a variable and n is an integer only. So this can be written as yn minus 1 divided by capital T. Now we can see that the system function where yt is the input and output is d by dt of yt, then the system function is hs is equals to s, because the output is differentiation of the input. Thus the system is hs is equals to s, because if the input is ys, then we know that the differentiation is written as s times of ys. So here hs is equals to s. Now similarly, if we look at the other side of the equation number, so let us say this is equation number 2. So when yn is the input, what should be hz? So that output is yn minus 1 divided by capital T. Now since we know that the input is yz, and output is yz into, by taking the z transform of this, we can see that 1 minus z inverse divided by capital T. So Hz will be equals to 1 minus z inverse divided by capital T. Now in this transformation, as we know that from equation number 2, this in time domain, that is dy by dt over dy by dt over t equals 20 is equal to yn minus 1 divided by capital T. So the system functions in analog domain of this operation will be equal to the system function in discrete domain of this operation. So we can say that S is equals to 1 minus Z inverse divided by capital T. Okay, so how we are getting this? Let me explain you one more time. So this is the equation that we get, and in time domain, in continuous time domain, and this is the relationship between the continuous time domain equation and the discrete time domain equation. And then we actually try to convert the time domain, continuous time domain into Laplace and discrete time domain into Z transform, and then we compare the two, that the systems doing the operation of differentiation in continuous time domain should be equal to the system doing this operation on the discrete time domain. So from there we are getting this. Okay, so the very important result is this, that whenever in any question we have to convert or we have to realize IIR filter using the derivative method, then S has to be replaced by 1 minus Z inverse divided by capital T. Okay, so S square will be equals to 1 minus Z inverse divided by capital T whole square. S to power I will be 1 minus Z inverse divided by capital T to power I. Okay, so if in any question we need to convert analog filter with transfer function h of as into digital filter using method of derivative, then simply h of z is equals to h of as, where s is equals to 1 minus z upon z inverse upon capital T. Now let us do the mapping. Between S plane and Z plane. S plane and Z plane. Now, since S is equals to 1 minus Z inverse upon capital T, so we can see that Z is equals to 1 upon 1 minus S into T. Okay. Now, since S is equals to J omega, where omega is continuous frequency, okay, or you can say the continuous time frequency. Okay, continuous time frequency, and Z is equals to R e to power, okay, sorry, S is equals to sigma plus J omega, where omega is continuous time frequency, and Z equals to R e to power J sigma, where sigma is discrete time frequency. So Z is equal to one upon 1 minus sigma plus J omega into capital T. Now if we talk about only the imaginary axis, so at imaginary axis of S plane sigma equals to 0, the real part. So z is equals to 1 upon 1 minus j omega t. So since z equals to 1 upon 1 minus j omega t, so in the magnitude form this can be written as 1 plus omega square t square, and in the denominator the angle will be minus tan inverse omega t. So in the numerator it will go as plus tan inverse omega t. This is your z. Now we can see that at omega equal to 0, z will be equal to a point in z plane at z equals to magnitude 1 angle 0 degree. Okay. And at omega equals to infinity, z will be a point on z plane at z equals to 0. Okay. So if you see the mapping, then you can see that omega varying from minus infinity to infinity correspond to locus of points in z plane is a circle with radius 1 upon 2 in center z equals to 1 upon 2 as shown below. Okay, so here I have pasted a figure that shows that the whole left half plane is mapped into a circle here. Okay, and thus the imaginary axis, this imaginary axis is mapped into a circle of radius 1 by 2, center 1 by 2. Okay, so this is the mapping. So now a very important point is that, so now we can see that using this, using the difference method to convert analog filter into digital filter, if the analog filter is stable and causal, then digital filter will also be stable and causal. Okay, because whenever any pole is on the left half of the S plane, the system is stable, and this is actually getting mapped into this circle. And in the Z plane, stability is when the pole is inside the unit circle and this circle is inside the unit circle itself. So the digital filter will also be stable. So this is a very important point. Next important point is that since the location of pole, this is very important, since the location of pole in Z plane is confined to smaller frequencies only. because the pole can be inside this unit, this circle only, the circle which has the boundary by purple. Okay, this circle only. And since the location of pole is, for example, P1 is written as magnitude e to power j phase, so we can say that the value of phase can be a smaller value only, because the pole has to lie inside the circle only. So we can say that since the location of pole in z plane is confined to the smaller frequencies only, thus this method is used for low pass filter and band pass filters only. This is not useful for high pass filter or band reject filter. So these two are very important points. In any competitive exam, they can directly ask you such kind of statements. Okay, so let's move on to another part of this method one. So there is one more method. So in the previous method, we have seen backward difference method. So now we will see the forward difference method. So what is this? So here dy t by dt at t equal to nt is written as yn plus 1 n plus 1 capital T minus ynt divided by t. So as we have written in the previous section also, so yn plus 1 minus yn. Okay, okay, so now we can say that S is written as z minus 1 divided by capital T. Okay, so this is the transformation formula, or I can say that z is equals to 1 plus st. Now if I do the mapping, if I do the mapping of imaginary axis of S plane into Z plane, so what will be happen? So at imaginary axis we have S is equals to sigma plus j omega and sigma is equals to 0. So in the Z plane it will be 1 plus j omega t, and since omega goes from minus infinity to infinity, so Z is equals to 1 plus j omega t. Now this can be seen as a, so Z equals to 1 plus j omega t, so we can say that the real part of Z is 1 and imaginary part of Z is j omega t. So the mapping of imaginary axis of the S plane is into a straight line on the Z plane like this. Now since we know that the mapping should be such that the mapping should be such that stable analog filter should give us stable digital filter, and we can see that here it is not happening because an imaginary part is j omega capital T. Now we can easily see that the mapping of this green region, that is left half of S plane, will be into this region of the Z plane. Okay, and we can easily see that this whole green part is stable for the analog filter, but this red part or the red region where this is mapping taking place is not stable for the digital filters. It is stable only inside the unit circle. Thus we can say that this kind of transformation, that is the forward difference method, will not ensure that the stable analog filter will lead to a stable digital filter. So that's why this kind of transformation is not good, and that's why this kind of transformation is not used in the computations. Okay, now let's solve one or two examples. And since the forward difference method is not good, so it's not used, we will always use backward difference method. So question is, analog filter transfer function is given 2 upon s plus 3. We have to convert into digital filter using the backward difference method. So we know that HAS, or we can say that HZ is equals to HAS, where S is equals to 1 minus Z inverse divided by capital T. So Hz is equal to 2 upon 1 minus Z inverse divided by capital T plus 3. So we can solve this and get 2 capital T upon 1 minus Z inverse plus 3t. Okay. Now generally in the question capital T will be given to us and we can easily find Hz expression from here. Okay. So similarly we can easily solve the questions. There are no issues. The only thing is that we have to replace S by 1 minus Z inverse divided by capital T, and capital T will be given to us in the question. So there is nothing much in such questions. You can easily solve them. Okay, so we have done method 1, that is backward difference method. We have already also talked about the forward difference method. That is not very good and it's not used. Okay, so thank you guys. In this part we will be talking about the second method to design the digital filter. Okay, so we have already seen the backward difference method, and here we'll be talking about the another method that is called impulse invariant transformation. Okay, that is called impulse invariant transformation, a very important transformation. Okay, so let's start with, so suppose we have an analog filter with impulse response HAT. So HAT is impulse response of analog filter. Okay. T is the sampling interval, and Hn is the impulse response . of digital filter. Okay, so impulse invariance transformation, I will be calling it IIT. Okay, so impulse invariance transformation. So Hn is equal to T equal to N capital T. Okay, so this is important. Okay, so this is actually the transformation, how to transform the analog filter into digital filter. So by simply sampling it. Okay, so this is IIT method, that is impulse invariant transformation method. Now suppose HAT has a transfer function HAS. Okay, so now let's say that HAS is equal to summation I equal to 1 to n AI upon S minus Pi. So I say that there are n number of poles in HAS and the location of pole is P1, P2, P3 till Pn. Okay. Now if I convert this into time domain HAT, we know that it will come out to be AI e to power PIT UT summation I equal to 0 to capital N. Okay. Now we know that in impulse invariance transformation, Hn is equal to HAT, where T equals to N capital T. So Hn will come out to be I equals to 0 to capital N AI e to power Pi N capital T U of N capital T. Okay. Now this can be written as, since variable is u, n is the variable, capital T is the sampling instant, it's a constant. So this can be written as e to power Pi capital T whole to power n u of n. That is your Hn. Now, okay, so this is the transformation that will get the result, the impulse response of the digital filter. Now if I take the Z transform of this, now as we know that a to power n un has Z transform 1 upon 1 minus a Z inverse. So Hz will be I equal to 0 to capital N ai upon 1 minus e to power Pi capital T Z inverse. So we can say that in S plane, if I have a pole at Pi, will convert into, in Z plane, pole at e to power Pi T. So we can see that here. Okay. So Pi pole will convert into a pole at e to power Pit in Z plane. Okay. So the pole transformation is pole in Z plane is equal to e to power pole in S plane multiplied by T. So this is the transformation of the pole. Okay, Z equals to e to power St. Okay, so this is actually the relationship. between pole in analog domain to pole in digital domain. Okay, so this is the relationship. Now we can see that since Z is written as R e to power j sigma, or this is the digital frequency, is equals to e to power the real part of S, the analog frequency into t. So R will be equal to e to power, sorry, there has to be, sorry, e to power sigma t, or just wait a minute. So R e to power j sigma is equals to e to power sigma t e to power j omega t. So R is equal to e to power sigma t, and e to power j sigma is equal to e to power j omega t. Okay, so very important relationship it is that the magnitude of Z is equals to e to power real part of S into t, and the digital frequency is equals to continuous frequency multiplied by capital T, that is a sampling instant. So these two relationships are very important. So they can ask you these relationships in a question directly. That is, in impulse invariance method, how the digital frequency and the continuous frequencies are related, and how the magnitude of Z is related to the real part of S. These two relationships are very important. Okay. Now if I look at the mapping from Z plane into, sorry, S plane into Z plane, okay. Now in the left half plane, in the left half of the S plane, sigma or the real part is less than 0. So the magnitude e to power sigma t, magnitude of Z, will be less than 1. Okay, will be less than 1. So if I look at the mapping, then I can say that this whole left half plane is mapped into a circle of radius 1 in the Z plane. So this is Z plane, this is S plane with real part sigma and imaginary part j omega. Okay, now, okay, so the whole left half of the S plane is mapped into a unit circle. So this is what we wanted, that is, the whenever there is a stable analog filter, it will always lead to stable digital filter. Okay, always. Okay, but one very important point here it is that if we look at this equation, this one, that in Z plane Z is equals to R e to power j digital frequency, and this digital frequency is always from minus pi to pi only. Okay, we know that because the digital frequency axis is periodic with 2 pi, with a period of 2 pi. So it is always between minus pi and pi only. But omega, that is the continuous frequency, is from minus infinity to infinity. Okay, so if I see the mapping, then sigma that is we got is equal to omega t. So one very important point is that sigma, that is the digital frequency, will be from minus pi to pi when omega is between minus pi by capital T to pi by capital T. So this will be equal to, so sigma will be from minus pi to pi when omega is between minus 3 pi by capital T to minus pi by capital T. So sigma of the digital frequency will be from minus pi to pi when omega is from 3 pi by capital T, okay, from pi by capital T to 3 pi by capital T. So what am I saying is omega will vary from minus infinity to infinity, but the digital frequency will be always from minus pi to pi only. So we can say that whenever there is a range of omega, so I can say that whenever omega is between 2k minus 1 pi by capital T to 2k plus 1 pi by capital T, where k is integer, then this will correspond to digital frequency that is from minus pi to pi. So we can say that where k is an integer, so we can say that there is infinity to many mapping. Okay, that is omega is going from minus infinity to infinity, and this whole is mapped into sigma minus pi to pi. Okay, so there is an infinity to many mapping taking place in this kind of mapping, that is inverse impulse invariance transformation. In IIT, the continuous frequency is mapped into the discrete frequency, but this mapping is not one to one, rather it is many to one mapping. Okay, so this is very important, and this does not take place in the method 3, which is bilinear transformation. We will be talking about in the part 4 of the lecture series. So this is very important property of the impulse invariance transformation that can be asked in any of the competitive exam. That's why I have emphasized here on this property of the impulse invariance transformation. Now let's look at one example, a simple example. So question is, it is given that HAS is equals to 1 upon, sorry, it's 2 upon s plus 1 into s plus 3 and t equals to 1 seconds. Okay, so we have to find the transformation. So using IIT, so HAS is equals to 2 upon s plus 1 s plus 3. This can be written as 1 upon s plus 1 minus 1 upon s plus 3. So this is HAS. This can be written as 1 upon s minus minus 1 minus 1 upon s minus minus 3, that is HAS. Now HZ, we know the transformation 1 upon 1, or let me write the transformation for you guys. 1 upon s minus pi is transformed into 1 upon 1 minus e to power pi capital T z inverse. This is the transformation formula. We know this formula. So from this equation, we can say that Hz is equals to 1 upon 1 minus e to power minus 1 Z inverse, because T is also, so in this case we can see that P1 is equal to minus 1, here P2 equals to minus 3. So capital T is 1 second, so we can say that here it is P1 into capital T, that is minus 1, and here it is in the second part we have P2 into capital T, that is minus 3 Z inverse. Okay, so this comes out to be 1 upon 1 minus E inverse Z inverse 1 upon 1 minus e to power minus 3 Z inverse. So we can easily put the value of e to power minus 1 and e to power minus 3. So we get that 1 upon 1 minus 0.36 Z inverse 1 minus 0.049 Z inverse. Okay, so this kind of questions can be asked in any of the competitive exam. So this much is sufficient in the case of impulse invariance transformation. So in the next part we will be looking at bilinear transformation. That will be the method 3, and that will finish the IIR filter design. So thank you guys.